All right, section 7, finding the derivative at a point. This section can be one of the hardest sections for people as far as number of retakes. It's not a difficult section, but it does require that you understand and implement this equation. This equation will be present on every version of this test. So, first, what is this equation trying to accomplish? Well, it's finding the derivative at a point. That's what this means. F prime of some constant. That's why we use c. So c shows up many times in our equation. We're doing the limit as our x value approaches that of the height of an x value minus the height at c over x minus c. Now this should be very recognizable. Anytime you think derivative, you should think slope, and this is a slope equation. It's y2 minus y1 over x2 minus x1. So that's y2, y1, x2, x1. And yeah, this should be pretty obvious that these are x's. F of things are usually heights of things on graphs, so it kind of follows that pattern. So let's talk about what this means. So we have some graph, and we have some curve, and we have some height. This is where we're trying to find our slope. So f of c and c. So we're c over and f of c up. That's what those mean in the equation. All right, we're going to pick some other point, f of x, and we're x over. So we're f of x high, so f of x is like here-ish. So that's our x point. Now what our equation says is we're zooming x towards c. So this is actually going towards here, and we're finding the limit as they get really close together, which should give us a pretty accurate, and in the case of a limit, exactly accurate answer for our derivative. So that's why this equation works. Now let's go into some implementation of this. So you need to be able to recognize this and then solve this kind of problem. That's kind of how this shows up. So here we have a limit, and notice these are the same format. Limit as x approaches c. Our c is 5, it tells us, because it's as x approaches c, so it's 5 in this problem. So c is 5. Now we need to find f of x. F of x is just whatever's here. It's x plus 1 squared. That was pretty easy. All right, now to solve this problem and figure out what the answer to this is, we should just use the derivative because this is a more powerful tool. So that's what we're going to do. We're going to find the derivative of this. So we pull down the 2 times x plus 1. Boom, that's our derivative. And now the whole point was to find the derivative at a certain value at 5, and so we just plug in 5 for x, and it's 5 plus 1 is 6, 2 times 6 is 12, and that's our answer. Don't try to do this another way. You'll be really sad. This one in particular might have been easier. You could expand this, you could probably factor it, you could probably cross out the x minus 5s, and it would work out. In fact, it definitely would work out because you'd get, let's not go into it. It's x minus 5 and x plus 7 on top, and then the x minus 5s would cancel out. But this is a more powerful way of doing this problem, and the way this will show up on AP tests and that sort of thing is often going to be in problems where it's very hard to factor this or impossible. And so you want to be able to use this tool, go, oh, I recognize this, let's go straight to this. All right, over here. This is the easier part. The blue line is the guy on top. On my website, it's more obvious which one's blue. The slope of this guy on the 8th is about 0. So yeah, it's about 0. That was a really bad about sign. So about 0. Then on the 18th, oh, did I mislabel my graph? I mislabeled the oh yeah, right, we're 18th, we're in between. So we're like about here. And that is it's fairly steep. There's hundreds along the sides. we're going down about 100 a day, so I went with about negative 100 for my slope. If I wanted to do units, somethings per day, it's not going to bother. We don't have it on all the axes. And now last, we're going to do the 15th for red. So on here, that thing is just going down really slowly. So I said it had about a negative 1.5-ish slope. On my website, I said negative 1.6. Again, these are ballparking. When it says estimate, we don't need to do it exactly right. We just need to be pretty close. And that's it.